Now, the outlines of this presentation is we are going to talk about what the aberrations are clinically, types of aberrations, principles of measurements, and clinical interpretations. Now, what are the aberrations? Actually, if we have a perfect refractive surface, such as a perfect cornea, then the wavefront, or let's say that the lights coming from the infinity will refract, and the wavefronts of these rays will take the shape of the refractive surface, and all will meet in a focal point. This is a perfect refractive surface, which actually does not exist. Let's see what will happen if the light will go through an imperfect refractive surface. What will happen is the wavefronts will not be focused in one point, but these wavefronts will take the shape of the imperfect refractive surface. Okay, this is an imperfect refractive surface. Now, as you see, these wavefronts in red, they are not curved, let's say, and they are not straight. So they are distorted. Now, to measure the distortion, the principle of measurement is to correlate this distorted wavefront or aberrated wavefront to a perfect wavefront, and to see how much it is deviated from this perfect wavefront. And this is the principle of the root mean square. As you see here, the deviation in the upper part is plus 0.25 microns, for example, while in the middle it is minus 0.40, and on the bottom it is plus 0.30. And then the root of the sum of this is the root mean square, RMS, which represents the deviation, but it does not represent the type. This should be put in mind, okay? We have to remember that the RMS quantifies but does not qualifies, does not tell us that this is comma, this is spherical aberration, this is trefoil. It just says that this eye is highly aberrated or slightly aberrated. Types of aberrations. If we look at the Zernike polynomials or the Zernike pyramid, we will find that the first two rows, N0 and N1, they are called constant aberrations, all right? Then there are low or lower order aberrations in the second row, N2, all right? Lower order aberrations, which are associated with refractive error, the astigmatism, myopia, or hypermetropia. So the lower order aberrations are of three types. The one in the middle is called defocus, which is associated with myopia and hypermetropia. And those on the sides are vertical and horizontal astigmatic lower order aberrations, which are associated with vertical and horizontal, or with the rule and against the rule astigmatism, respectively. Then we come to the higher order aberrations. Higher order aberrations start from N3, okay, and downward. Usually, until the sixth row are considered significant. Otherwise, N7 and after, they are not taken into consideration in the treatment or in the diagnosis because they have very, very insignificant impact. Okay, we have to know that this pyramid has two rows of numbers. The first one is N, okay, for on the left side, and M, which is on the bottom. Whenever you see M in minus, it describes vertical aberrations. And whenever you see M in plus, it is considered as horizontal aberrations. All right. So as you see, the numbers, all numbers on the right, are considered in the for the higher order aberrations. For the M, they are n plus. The M, I mean the M. I don't mean the number under the higher order aberrations or the symbols. So just keep in mind that M, whenever it is n plus, then it represents horizontal aberration. And whenever it is n minus, it represents vertical aberration. We come to the pyramid again. Now, you will find that any aberration, look at this pyramid, any aberration has a symbol. This symbol is Z, and then there are two numbers. One upper superior one, which is -2, for example, and an inferior one, which is 2. Okay, let's see what do they mean. So we have Z, M, and N. M in red and N in blue. Okay, let's see the definition of these two. What do they stand for? The N stands for a radial function that is proportional to the order of the polynomials. And M, the red one, stands for a continuous function that repeats itself every 2 p radians. Okay, here you can see me smiling because did anybody understand anything of this? I'd like to hear or to see whether anybody can tell. Okay, let's repeat. The N stands for a radial function that is proportional to the order of the polynomials. And the M stands for a continuous function that repeats itself every 2 p radians. Again, did anybody understand anything? From the audience? I'm asking the audience. Okay, great. Somebody is raising hand. Yes, please, Dr. Muhammad Munir. And
Kindly
unmute
unmute yourself. Thank you.
Yes, Muhammad Munir.
Yes, I can't differentiate between N and M. Also, I can't understand this.
Yeah, tell me, please. But please, if you have seen my videos, then okay, you are fine. You can understand them. But if not, let me know.
I can't understand. I can't understand.
You cannot. Okay, okay, great. Thank you for your input. Okay, actually, why I put these two definitions? Because these are the definitions found in textbook and in the internet and in the articles. But nobody can explain what do they mean because they are pure physics. This is why I sat for a long period of time to find what do they mean. And I will show you my definitions. M means the number of affected meridians. Just keep it in mind. I'll show you examples now. Number of affected meridians. So M, meridians. N, number of slopes along the affected meridian. All right? So we have meridians and there are number of slopes. Okay? Number of slopes along the affected meridian. Let's see what does this mean. Okay, let's take this high order aberration. This is, sorry, this is low order aberration. This is the astigmatic. Okay, the astigmatic, vertical astigmatic, low order aberration associated with the rule astigmatism. Okay, what does it mean? Number 2, N2, means there are let's start with the red one. Okay, the meridian -2. Minus, it is vertical. All right, so 2, it means that there are 2 cardinal meridians, 2 cardinal meridians, 2 main, okay, principal meridians, 1 and 2. If you see the 2D display on the left. Now, if you look at the 3D display of this aberration on the right, you will find that there are 2 slopes, 1, 2, on each meridian. Okay, this is why it has number 2 in blue. All right, so whenever you see the lower number, which means the order, okay, the lower number stands for the order. 2 means 2 slopes or 2 distortions, 1, 2. And the upper number, which is -2 in red, it means how many meridians are affected with these distortions. Minus is for vertical, plus is for horizontal. All right, now let's take another one. As you see, this is Z4 -2. 4 means it is from the 4th order. 4th order means there are 4 distortions, as you see on the 3D display on the upper right. You will find 1 going down, 2 going up, 3 going down, 4 going up. So there are 4 distortions along the affected meridian. And how many meridians? There are 2 meridians. Okay, so as you see, Z4 -2, minus, it means vertical. 4, it means 4 distortions. So it is from the order 4. 4 distortions means it is from the 4th order. 5 distortions, it is from the 5th order. 6 distortions, it is from the 6th order, and so on. Okay, so when you hear, let's say it an opposite way. When you hear that this is from the 5th order, it means there are 5 distortions along the affected meridians. Okay, N5, 4th order. Now, what about M? M means how many meridians are affected. Minus for vertical, plus for horizontal. So it is very, very easy. Now, this is another one, which is the defocus. It is associated with myopia or hypermetropia. So Z20, okay? Z20 means 2 slopes or 2 distortions, okay, along the affected meridian. But M0 means there is no meridian. So it is spherical. It is spherical distortion. So it is defocus because it is N2, but if it was N4, then it is spherical aberration. This is another example. Z5, 1, there is no minus, it is plus, so it is horizontal. Okay, 5 means 5 distortions along the affected meridian. If you see the 3D on the upper right, you will find 1 going up, 2 going down, 3 going up, 4 going down, 5 going up. And 1 in red means only 1 cardinal. I'm talking about cardinal meridians, because the perpendicular one, which is 90 degrees, it is not affected at all. There is no distortion. So it is not put into account. So when you see Z5, it means 5th order. 5 distortions along the affected meridian. Okay, how many meridians? It is only 1. And because it is plus, it is horizontal. So it is very easy. So this is these are my definitions. Okay. Now we come to the types of aberrations. As I said, lower order aberration and high order aberration, higher order aberration. The lower order, we have defocus and astigmatic, vertical and horizontal. So only 3. We come to the higher order aberrations. There are so many, but there are 3 main, 3 cardinal, which are spherical aberration, comma, and trefoil, from which other aberrations are derived. We have to put in mind that 90% of the aberrations in the normal eye are lower order aberrations, which means that they are associated with refractive errors, and only 10% from the higher order aberrations. Okay. Now, the higher order aberrations, 98.2% of them, okay, of aberration arises from the anterior corneal surface. So the anterior corneal surface is the main source of higher order aberrations. The posterior corneal surface has an insignificant role in the normal eye, but this role becomes higher when the cornea is distorted, but of course, not as much as the participation of the anterior corneal surface. So the anterior corneal surface is the main one. This is why topography guided treatment depends on the anterior surface, the information of the anterior surface. It does not take the posterior corneal surface into consideration. This is what you have to put in mind. And of course, when I say topography guided treatment, it includes what is called the corneal wavefront guided, because there is no corneal wavefront guided. It is actually corneal topography guided. There is no pure corneal wavefront guided. Wavefront guided treatment means only the ocular wavefront guided treatment. Okay. Now, I'm not going to talk about lower order aberrations because they are very simple, defocus and astigmatic. But what about the spherical? The spherical aberration, they cause the halos. They are the main source of halos. Of course, number of halos depends on 2 factors. Factor number 1 is the severity of the spherical aberration. And factor number 2 is pupil size. If the eye has high spherical aberration, when the pupil dilates, then the eye will suffer more from the spherical aberration. And this is what happens usually in the old excimer laser machines when the ablation was just in the center and the traditional zone was very, very simple. The profile was the monoline, not the optimized. Okay, so all of those eyes had spherical aberrations, but in different degrees based on the number treated and based on the optical zone treated and based on their pupil size. So at night, when the pupil dilates, those people used to suffer from halos. We come to the comma. The comma causes, or let's say, what is comma? The comma, as you see here, there are 2 meridians, principal meridians or cardinal meridians. The first one is, for example, this is, by the way, this is the horizontal comma. Okay, it is horizontal comma. Why it is horizontal? Because the distortion is on the horizontal meridian, and the vertical meridian is just straight away. So this is comma. Okay. Now, if you can remember, the comma is Z31. Why it is 3? Because 3 distortions along 1 meridian. Okay. People suffering from comma, they see this if they look at a spotlight. All right, they will see this comet. We come to the trefoil. Okay, trefoil people will suffer from, like Mercedes-Benz let's say, a symbol. Actually, the trefoil affects the peripheral vision, while the comma affects the central vision. The spherical aberration affects the peripheral vision, but this does not mean that they do not affect the vision in general. What I mean is the trefoil affects the whole vision, but mostly at the periphery. The comma affects the whole vision, but mostly in the center. And the spherical aberration affects the whole vision, but mostly at the periphery. Trefoil, of course, the name came from this trifolium plant. The trefoil causes the starbursts. Okay, you see when a patient looks at the light, especially at night, when they are driving at night, they look at the oncoming lights, they will see the starbursts. Of course, higher order aberrations cannot be treated by glasses or by the usual contact lenses. Principle of measurements. There are three types of measurements: the point spread function, PSF, the root mean square, and the modulation transfer function. Now, the PSF, by the PSF, you can see two things actually. The first one, you can see what the patient sees. Okay, so you can imagine what the patient sees and the severity of this, because if you look at this grading, you will find that minutes on arc down and on the left. So the more numbers, this if the distorted image is distributed on a wider range, it means that it is severe. Whenever it is distorted on a smaller range, it means that it is insignificant or small. Now we come to the number, which is efficient blur. Look at the red arrow, 0.41, so half a diopter. This is an estimation from the machine, okay, from the topographer or from the wavefront aberrometer. It is an estimation of the amount of distortion in diopters, okay? But it does not mean that if we put 0.5 diopters in the glasses, then this will disappear. But it is an estimation of how much it is distorted. Root mean square quantifies, okay, as I told you before, it quantifies, it gives the quantity of the aberrations, be it lower order aberrations or higher order aberrations or total aberrations. And it can be expressed in microns and can be expressed in diopters. But however, it does not give an idea about what the aberrations are. If the patient, for example, if RMS is 1 or 1.2, which is too much, it means that the eye is very much aberrated. Okay, but does the patient suffer from spherical aberration? We don't know. Does the patient suffer from comma? We don't know. So it gives an idea. And it can give everyone, one by one. We come to the modulation transfer function, the MTF. Now, this tests the contrast sensitivity. Okay, so let me be direct to the point. It examines the contrast sensitivity, all right? Because what is contrast sensitivity? It is the ability of the eye to discriminate between two lines, okay, at a given distance, or 2 points at a given distance. Now, when the eye can discriminate the 2 points, and these 2 points are, let's say, apart, widely apart, And then when these 2 points come closer, then the eye can see them just to only 1 point. This reflects how much contrast sensitivity this eye has. All right. So when the closer the 2 points, and although they are very close to each other, and the eye can differentiate or discriminate between them, it means this eye has high contrast sensitivity. All right. So, okay. Now, it is measured as a unit. Let's say that whenever it is 1, it means it is perfect. Let us see this one. So perfections, whenever you see MTF equals 1, it means perfection. Whenever it is 0, it means imperfection. And in the middle, it is 0.5. So according to that, you can qualify how much contrast sensitivity the eye has. And of course, you can measure contrast sensitivity by some charts. The charts should give the same size of letters, but with shading, with the contrast is going down and down. And if the patient can see the last one, it means 1. So the MTF is 1. If not, he can see 0.9, it means MTF is 0.9. So there are 2 ways, either given objectively by the machine, it can give you MTF equals so and so, or subjectively, you check it by some kinds of charts. Okay. What is the effect of low vision contrast sensitivity? Now, what's the importance of contrast sensitivity? The contrast sensitivity reflects the quality of the optical system. When the optical system is of very high quality, the contrast sensitivity is very high. So this is very important, of course, in refractive surgery, because it is very well known that when we do corneal refractive surgeries, we are affecting the contrast sensitivity. Of course, in different amount, based on how much we are treating, what technique we are using, and so on. The laser profile, of course, the laser spot profile, energy, size, a lot of things. In addition, for the intraocular refractive surgery, for example, premium lens, these premium lenses, they differ as well by how much they affect the contrast sensitivity. Now, if the patient has low contrast sensitivity, then he will suffer from problems in driving in the rain or at night. There will be difficulty pouring coffee into a dark mug. There will be difficulty in walking down the steps. Can you imagine? This is related to low contrast sensitivity, because the difference between steps should be discriminated by the eyes or differentiated by the eyes in order for the brain to know where to put the feet. Now, difficulty in focusing on small fonts, and eyes easily tiring while reading or watching television. So all of these symptoms, as you see, are not only related to higher order aberrations, but as well to contrast sensitivity. I will show you some of the clinical interpretation of the wavefront. Of course, why we should study wavefront of every patient coming for refractive surgery, because we can explain the symptoms, we can know what symptoms he has. We can decide the best profile in laser-based refractive surgery, whether it is optimized, the usual one, or customized, wavefront guided or topography guided. In addition, wavefront is used in presbyopia treatment when we do the laser-based presbyopia treatment, because some profiles change, or some methods change the asphericity of the cornea. Now, they help us in the higher order aberrations, I mean, or the wavefront, helps us in selecting the monofocal, IOL monofocal, whether it should be spheric or aspheric. And if it is aspheric, whether it should be asphericity 0, asphericity minus 0.27, or asphericity minus 0.20, which is the algorithm. To do or not to do premium IOL implantation, because if the eye is very much aberrated, we cannot implant premium IOL implantation. As I told you before, we can explain the symptoms of the patient. I'm not going to talk about to decide the best profile in laser, because this will be the third, inshallah, the third presentation. In presbyopia treatment, I'll show you the principle of the spherical aberration, the importance of the spherical aberration, and the depth of focus. Okay, now let's remember these numbers: 0, 35, 0.35, and 0.6 microns in microns, okay? Remember, plus and minus. The human cornea ranges between 0 and almost 0.50, almost, microns plus, with an average of 0.27 microns plus minus 10 microns standard deviation. So this is the normal cornea. So the normal cornea has positive spherical aberration. Okay. Now, the spherical aberration is not proportional to Q value, but as well to the radius of curvature. So K readings. So we cannot guess the spherical aberration just from the Q value. The Q value describes the asphericity, all right? If we say that Q value is, for example, minus 0.5, there is no equation or formula that says, okay, Q plus minus divided, multiplied, so on, then spherical aberration is. But it is related, the spherical aberration, it is related to the K readings as well. So spherical aberration related to the shape of the cornea and related to the K readings, the power of the cornea. All right. Now, whenever there is, let's say, let's look at the Q value. When the Q value is minus 0.53, it means that there is no spherical aberration. We call this shape the parabola, or the perfect prolate. All right, this is the eagle eye, eagle cornea. Now, the human cornea ranges between this and the plus. Whenever Q value is more positive, for example, Q minus 0.2, for example, it is more positive, then there will be positive spherical aberration, and vice versa. Myopic treatment will push the spherical aberration to more positive, while hyperopic treatment will push spherical aberration of the cornea towards more negative. Now, you may ask, okay, what about these zones? The red one, the green one, and the gray one. So the clinical application of the spherical aberration is increasing the depth of focus in presbyopia treatment, selecting best monofocal IOL, as I told you, in PSIS algorithm, and for the customized laser vision correction. Okay, now let's talk about the depth of focus in this lecture. Then I will answer the question, what about the zones, the red, green, and gray? The depth of focus, as you see, let's assume that this old gentleman has no accommodation at all. And he uses reading glasses to read at this distance. For example, if he uses plus 2.50 diopters to read at this distance, okay? Now, if this patient has depth of focus, it means if he moves the book backward and forward within a given range, he can still see the book clearly, although he is not using accommodation at all. This is called depth of focus. All right? Now, what's the importance of depth of focus? Now look at this video. Now, if the eye has no depth of focus and no spherical aberration, then if the letter, let's assume that this eye is emmetropic, okay, emmetropic, and the letter is at infinity or 5 meters, for example, then it will be very sharp image on the retina and very sharp image in the brain. Now, what if this patient does not have any spherical aberration and therefore no depth of focus, and this letter moves? What will happen? If it moves, then there will be out of focus. Forget about the accommodation. We are not talking about accommodation. Let's say that this eye does not have accommodation. All right? So, as you see, as the letter moves to the front, forward and backward, it will be blurred on both on the retina and in the brain. Okay? Now, let's assume that there is some spherical aberration, which means depth of focus. Okay. Now, although the image on the retina is a little bit blurred because of the spherical aberration, but the brain can compensate by neural adaptation and can see the letter sharp, okay, as sharp as if there is no spherical aberration, all right? But this would be to some extent, and this is the non-toxic spherical aberration, okay? Now, what is the benefit of this spherical aberration if it is non-toxic? It means, or it helps, that if the letter moves forward and backward, although it is a little bit more blurred on the retina, but it will stay clear in the brain, all right? Look at this. Now it is moving backward and forward, and it is still very clear on the brain. But if it moves out of this range, then it starts blurring on the brain. All right? Now, there is a threshold beyond there will be blurriness even without movement of the letter, like in this case. Okay? Look at the image in the brain. Now it is blurred. Okay? So, as you see, let's look at this slide. So, let's say that if the spherical aberration is within 0.35 plus minus, we call this normal or usual, which everybody can tolerate. Now, if it is in the green zone, it is the non-toxic, okay? The non-toxic between 0.35 and 0.6. Now, it is non-toxic, which means that if anybody has it, then there will be neural adaptation and there will be like the brain can see sharp as well. But if it is beyond 0.6, it is toxic and the brain cannot tolerate it. Now, there is a correlation between, or an inverse correlation between the contrast sensitivity and spherical aberration. Contrast sensitivity is very high when there is no spherical aberration, when Q value is minus 0.53, or, as I told you, the parabola shape of the cornea, the eagle eye. The contrast is very, very high. This is why the eagle can see any target, which is away, although it is very away, very, I mean, on very large distance, because the eye can discriminate the points very sharply. Now, the contrast sensitivity will go down more and more, let's say, will be less and will be worse with the increase of the spherical aberration, as you see here. Now we come to the depth of focus. As we saw in those videos, there will be no depth of focus if the spherical aberration is 0. The depth of focus increases with the increase of the spherical aberration. But to some extent, whenever the spherical aberration becomes toxic, then depth of focus will be very much affected, almost no depth of focus, because the image will be very blurred. Okay? Now, the three major higher order aberrations are the spherical aberration, comma, and the trefoil. And these three are to be studied in every patient, okay, individually and all together. So how to study the Zernike analysis of the Pentacam? Just a second, let me switch the power on. Okay, now as you see, this is the Pentacam giving the Zernike analysis. Before we study, we have to be sure that it is Zernike order 6. It is not more. Maximum diameter is 6 millimeter. We click on the pyramid, not on the list, not on the normalized. And we click on wavefront aberration of the total cornea. We have to study the total cornea, not only the anterior surface or posterior surface. Okay, so remember 6 millimeter and up to 6 order only. No need to study more than this. Okay. After that, we click all of them off, and then we click on only 5, as I told you. The vertical trefoil, the vertical comma, the horizontal comma, the horizontal trefoil, and the spherical aberration. We click them on, all right? Now, then we have 2 numbers to look at. The first one is the RMS. This RMS is for those 5 higher order aberrations, because we click them on and all others are off. If you don't click these on and all others are off, then the RMS will represent what's on, all right? So in many cases, when some friends send me some of these to study, I find that all of them is on. So I cannot study. We have to click on all, only these 5 higher order aberrations. And we have to look at the, and we have to look at this one, if you can see the mouse here, the Z40 or the spherical aberration, okay, alone, because it has a meaning when we study both, the RMS in total and the spherical aberration alone. Now, the spherical aberration alone here, it is not displayed in RMS. It is displayed in what is called Zernike coefficient. This is why you see Z40, Zernike coefficient, all right? Of course, I'm not going into details in this very quick lecture, but however, remember, the Z40 means Zernike coefficient. Okay, this is an example. The total is 0.34 microns, the total of the 5, okay? And the spherical aberration is 0.31. Now, because the total is less than 0.35, this patient does not need customized laser vision correction. He just needs optimized. And if we are planning for phakic IUL, we can implant the phakic IUL comfortably because the patient doesn't have high order aberrations and we are not going to complicate the case. And if we are going to implant monofocal, of course, to understand what I'm presenting now, the zero spherical aberration and so on, you have to know the PSIS algorithm. Now, it is available in my videos. So if we are planning to get benefit of his spherical aberration, which is 0.31 for depth of focus, so we have to keep it. So we implant a monofocal, which is zero spherical aberration. Okay, so to keep it. If we keep it, the patient has some depth of focus. But let's assume that this patient is a cataract patient and we are going to remove the cataract, okay? So we are going to implant, for example, monofocal. If we leave his spherical aberration, then he will get benefit from the depth of focus. So we implant zero spherical aberration. Now, if we don't want to keep his depth of focus and we want to give him very sharp vision and get rid of his depth of focus, then we have to compensate for this. How to compensate? We implant a monofocal with negative spherical aberration. For example, minus 0.27 spherical aberration. So it will compensate for this. So he will be very close to zero, very sharp vision, but no depth of focus. Or we can implant premium IOL because the total is less than 0.35 microns. This is another example. This patient has 0.68 microns in total, which is high. And the spherical aberration is very small. So most is because of vertical trefoil and horizontal comma, as you see. So the patient has high order aberration on account of trefoil and comma, not the spherical aberration. And the patient is suffering from symptoms. So if we are planning to do LASIK, then either topography guided treatment or wavefront guided treatment. All right. When I say wavefront guided treatment, it means ocular wavefront guided treatment because there is no corneal wavefront guided treatment. The corneal wavefront is topography guided. Okay. Do you see how important is to look at or to have a look at the Zernike analysis for every LASIK patient? Now we come to the phakic IOL. We can implant it, but we will tell the patient that your symptoms will stay because we are not going to change the high order aberrations. If the patient has, for example, cataract and we are planning for a monofocal, okay, sorry. Yeah, this one. Yeah, if we are planning for lens implantation, it should be monofocal. We cannot implant trifocal or EDOF to this patient. So no premium IOL for this patient. This is example. This is not from the Pentacam. It is from Cyrus. It gives the numbers in a different way. So it gives the total, okay, but all total, not for the 5. This is the problem with the Cyrus. You cannot select, okay? In Galilei and Pentacam, you can select only the 5. Here, it gives everything all together. This is why I raised the threshold a little bit in the Cyrus. What do I mean by this is, I usually exclude or decide that the patient has significant high order aberrations if the total is more than 0.35 microns, okay, in the Pentacam and Galilei, because I am selectable to those 5 high order aberrations. But in the Cyrus, because it's giving from N3 and downward, I cannot select, so my threshold is 0.5 microns. I will say that the patient has significant high order aberrations if the total is more than 0.5, not more than 0.35, because if you say more than 0.35 in the Cyrus, then you will exclude all patients. Now, it gives as well the comma alone, it gives the spherical aberration alone, and it gives others called residual, which means that trefoil and the others going down in the Zernike. So it is not only trefoil. Residual does not mean trefoil. It means all others. Okay. Now this patient has high, more than 0.5, because this is Cyrus, and has symptoms. Okay, so we have to go for topography guided treatment or wavefront guided treatment. We can implant phakic IOL, but we have to tell the patient that you will not get rid of your symptoms by the phakic IOL. Phakic IOL just to get rid of glasses, which is lower order aberrations. And if he has a cataract and we are planning for cataract, we cannot implant premium. It is just monofocal. And by the way, the monofocal, when the patient is suffering from higher order aberrations, it's better to put the monofocal with spherical aberration 0, which means that we do not complicate his eye. We do not add spherical aberration or deduct spherical aberration, all right? We just keep his high order aberrations as they are when we implant a monofocal with spherical aberration 0. This is example, another example. Of course, you see that the numbering of the examples is different. So clinical example 5, however, because they are from the from other presentation of mine. Now the total is 0.53 borderline on account of spherical aberration, which is 0.44. So very interesting case. The patient doesn't have symptoms, and we are planning for LASIK. Okay, we can do it optimized, so no worries. Phakic IOL, it will be okay. If the patient has cataract, as I told you, you can leave the patient with his depth of focus because his spherical aberration is very good, 0.44. So he is in the green zone, which is non-toxic. So he has depth of focus, good depth of focus. So he can use his depth of focus for reading maybe large fonts without glasses, okay, if we implant the monofocal. So in this case, I'm going to implant a monofocal with 0 spherical aberration in order to keep it. But if you are planning to give him very sharp vision and get rid of his depth of focus, okay, you can implant monofocal with spherical aberration minus 0.27 to compensate for this, and he will still have plus 14 microns of spherical aberration, which may help him to somehow, but not as good as having spherical aberration 0.44 for the depth of focus. So this is a quick overview. There is a lot of things that we can